In this video, we're going to look at an idea called Lagrange multipliers. And the goal of what we're doing in this section is to maximize or minimize a certain function f subject to a constraint that looks like function g equals a constant. The Lagrange multiplier method works like this. We're going to let the gradient of f equal lambda times the gradient of g. And lambda in this context is a constant. In fact, it's called the Lagrange multiplier, and that's where the name of the technique comes from. So the idea is that by saying gradient of f equals lambda times the gradient of g, that's going to produce a system of equations that we can solve to find the point at which our function is maximized and to find the maximum value of our function as well. So here's the problem that we'd like to solve. We want to find the points on xy equals 6 that are closest to the origin. Let's draw a picture, see what that might look like. So xy equals 6 is a hyperbola. Let's say it looks something like this. And we want to locate the points on the hyperbola that are closest to the origin. So maybe here and here. Looks to me geometrically like we'll have two different answers to the problem. So we mentioned in our introduction that we use the Lagrange multiplier method to either maximize or minimize a function. In this case, we are trying to minimize, and what we're trying to minimize is the distance to the origin. So we're trying to find these 2 points here that have minimum distance to the origin. Okay, well, we need to introduce some variables so that we have something to work with from an algebra point of view. So we could say, let the points be xy. And as we can see from our picture, there are going to be a couple of different answers, a couple of different points that satisfy this. So that's fine. When we go through and solve our system of equations, we'll have a couple of different possibilities for x and y. Now, the function that we're trying to minimize is the distance between our points and the origin. So let's just label this top point here. Let's call that xy. This point here, that's our origin, so that's 0, 0. And distance, if we think back to maybe pre-calculus where we saw a formula for distance, square root of x2 minus x1 squared plus y2 minus y1 squared. And if we actually just sub into this, let's say xy is acting as our x2, y2, and let's say 0, 0 is acting as our x1, y1, then we'd have a formula that looks like x minus 0 all squared plus y minus 0 all squared under the square root. Or more simply, we could just call that the square root of x squared plus y squared. So if you thought about this in a linear algebra context, you could say, oh, this vector from 0, 0 to xy, that's just the vector xy, and then we're just talking about the length of that vector. That would certainly be a faster way to come up with that distance. And whether we're looking at the top point or the bottom point in this diagram, distance formula is the same. And as we mentioned, if there are two possible points that work, what's going to happen is we'll have two different solutions come up in the answer. Now, when we get into the calculation, there are going to be partial derivatives involved. So a nice trick here is to modify the function that we're trying to minimize. So it's actually equivalent to minimize distance squared. And the reason why you might want to do that is because it would remove the square root from this quantity. It makes taking the partial derivatives way easier. So we could then call this d squared, or if you want, you could just call it f, since that's the function that we're actually going to minimize. So while d and f have different values, they both yield the same points at the end of the day. Whatever combination of x and y values makes f as small as possible is the same combination of x and y values that makes d as small as possible. So we are good to go, and I'm going to highlight this. That's the function that we're trying to minimize. So constraint or restriction on the xy values, the idea is that xy can't just be any old point. If we look back at our problem and our picture here, remember these points needed to be on the hyperbola. So the constraint is actually just coming from the equation of the hyperbola, xy equals 6. And we'll just give a name to this left side of the constraint. We'll call that g. So the constraint always has to have the form g equal a constant, so g will be xy. Okay, and with that, we're ready to jump into the calculation. So we said at the beginning of the video that the way the calculation is going to work is we're going to take the gradient of f and we're going to set that equal to lambda times the gradient of g, where lambda is some constant. So let's try that. F is the function x squared plus y squared. So its gradient is 2x, 2y. We're going to say that's equal to lambda times gradient of g. Okay, well, if g is equal to xy, then its gradient is y comma x. So this leads us to two equations. If we look at the first components of the vectors, this is saying 2x equals lambda times y. That's one of our equations. And then second equation comes from the second component of these vectors here. So 2y equals lambda times x. So we've got two equations in technically three unknowns. We've got the x, y, and the lambda that are unknown. There's actually a third equation, and that's really our constraint. So remember our constraint g that we wrote down a little bit earlier, xy equals 6. So the reason I'm writing the constraint on the side here is just that it doesn't involve a lambda, so it's a different type of equation than the first two. So I'll show you a general procedure here that will work anytime you have one of these two variable Lagrange multiplier problems where you've got an x, y, and a lambda coming into the problem. What we can do is we can solve for lambda in each of the equations, and then we'll be able to set lambda equal to lambda. So from equation 1, let's solve for lambda, 2x over y. And from equation 2, let's also solve for lambda. Lambda would be 2y over x. Okay, so now we can say lambda equals lambda. So 2x over y must be equal to 2y over x. And we can cross multiply here just to turn that into a nicer looking equation. So we could have 2x squared equals 2y squared. Let's divide by 2. So y squared equals x squared. And we can take square roots of both sides as long as we acknowledge that there's a plus or minus sign option here. So y can be equal to either plus or minus x. So we've already made quite a bit of progress here, and the equation that we haven't used yet is the constraint. So let's look back just a little bit higher on the screen here. Actually, it might be a good idea to put a box around the three equations so that you can find them later when you need them. So let's think about this equation 3 now, this fact that xy equals 6. Okay, so if xy equals 6, that actually implies that x and y have the same sign. So they're either both positive or they're both negative, because when they multiply, they create a positive number. So that actually rules out the possibility that y could be equal to negative x. We actually must have y equal x. Okay, so already just by looking at that constraint, we've got a bit more information. And in fact, if we now plug y equal x into our constraint, we're going to get exactly our x values. So let's put y equal x into that equation 3. Equation 3 said xy equals 6, but if we actually replace the y with the x, this is going to read x squared equals 6, which means x can be either plus or minus root 6. Okay, and then just to give a complete answer in terms of our x and y values, remember we decided up here that the y value would always be equal to the x value. So if you have the option, it's always good to break it into cases. If you have the option x equal root 6, because y is equal to x, the y value that goes with that will also be root 6. And if x equals minus root 6, again, because y equals x, the y value that goes with that minus root 6. So there we have our 2 points. Here's our solution coming up. So xy can be either root 6, or the negative version of that. So you could actually just write plus or minus root 6. So just to make that look like a final answer, I'll say the points are plus or minus root 6. So let's scroll back to our picture quickly and just see if that seems reasonable. Well, certainly you can see from the picture that there are two solutions, so we found those. We don't have any scale on our diagram, but you can see that there is some symmetry there where those lines look, or those points look like they would lie on the line y equal x. So it seems reasonable that the y values and the x values would be equal for our 2 points. So that's our first example of doing a Lagrange multiplier calculation. And I just wanted to talk really briefly, a couple minutes, about how this method works. The Lagrange multiplier method selects the level curve of our function f that's tangent to the constraint. So let's draw a picture just based on the example that we just did. Okay, so our constraint was that our points had to lie on that hyperbola xy equals 6. So let's draw our constraint here in black. And then let's think about our function. What were we trying to do? We were trying to minimize f, which was x squared plus y squared. So remember when we say level curves of a function, you're just saying take your function and set it equal to a constant. So let's start drawing some level curves of f. Okay, if we had constant equals 0, we'd have just a circle of radius 0. In other words, the origin. There we go. If we had this x squared plus y squared equal 1, we'd have a circle of radius 1, etc. So our level curves of f are just these circles centered at the origin of different radius. Okay, now eventually, if we keep drawing circles here, eventually we will get to a circle, maybe it's going to be this next one, that will actually be tangent to our constraint. And so when the level curve of your function is tangent to your constraint, that means that you have actually made your function as big or as small as possible, depending on whether you're doing a maximization or minimization question. So you could even imagine having bigger circles out here that overshoot the constraint. Okay, so there's a special place where the level curve of f is tangent to our constraint, and geometrically those points of tangency correspond to the solution to the problem. Okay, so that's geometrically what's happening. Now let's connect that back to the formula. So you may remember from one of our previous videos that the gradient of a function is actually perpendicular to a level curve. So if we talk about these level curves of f, we know that the gradient of f is perpendicular to the level curve of f. And because our constraint is also a level curve, it has the form function equal constant. Also true that the gradient of the constraint is perpendicular to that constraint. So I'll just draw a gradient of g going this way here. So that black arrow there, that's our gradient of g. Okay, they may be facing same direction, they may be facing opposite directions, but the point is that at the point of tangency, at the point that we're interested in finding the solution to, those gradients will be parallel. And mathematically, when you have two vectors that are parallel, you're saying, well, they're multiples of one another. So we're saying gradient of f must be equal to some multiple of the gradient of g. So by writing down this equation, you're capturing the fact that the gradients are parallel, and that's capturing the fact that the level curve of f is tangent to the constraint at that point, and that's capturing the fact that you've maximized or minimized your function. So that's the geometry behind Lagrange multipliers. Thanks for watching.